the things we want to find, so equations we're going to need to develop, they include these unknowns. We want to find here what the tension is in the wire AH. So we'll find, I'll call it TAH. And we have a supported C, a supported D. We want to know the reactions at bearing C and bearing D. So reactions at C, reactions at D. And some extra information we're giving here. They tell us that the piece AB or segment AB is 250 millimeters. Which will also be noted in the free body diagram, since we'll want to be marking coordinates of points for this problem. In this case, what's the object that we're going to isolate for our free body diagram? All right, the shaft, and we're going to take just that. We're not including the bearings, so we'll model what the bearings do to the shaft we keep, and we're not including the rope in our picture, so we have to model what the rope does to the shaft. I'll keep the coordinate system that they have centered at B. All right, so the shaft goes from B through C through D, takes a turn at point E, and then F is where it terminates, and then on the other side of B, it goes into the YZ plane at a 30-degree angle. All right, so right now I just have the shaft. Now what I'll put on here, I'll start with the applied load, since those are going to be the easiest. We have one applied force acting on it at point F, and that's in the negative Y direction at 400 newtons. At A, because we're not including the rope in our picture, I have to model the effect that the rope has onto the shaft. Ropes only will impart a force along their length. So from A to H, we'll have a force pointing from A towards H, and that's the tension in AH. Okay, so that's the easier step. Now we want to model what the other supports are doing. Since we, again, did not include the bearing in the picture at C or D, we have to include what they do. At point C, the text tells us that it is a thrust bearing. So what motion is prevented from the thrust bearing at C? All bearings are going to prevent the shaft from moving normal to the longitude of the shaft. So in this case, if the shaft is along the X direction, that means that both bearings, whether it's a journal or a thrust bearing, will prevent it from moving in these YZ planes, since that's the plane normal to the X direction. So at C, whether it's a thrust or a journal, there'll be a component of force in the Z and a component in the Y. So I'll call that CZ, assuming positive in the Z direction, and CY, assuming positive in the Y. Now we want to consider the rest of the reactions. It is a thrust bearing, so what other motion does it prevent? Right. The difference between the thrust bearing and the journal bearing was that the thrust bearing also prevents the shaft from moving through the bearing or moving along the longitude of the shaft itself. So at C, that thrust bearing, there'll also be a force because it prevents motion in what is the X direction. There'll be a force in that X direction. So this will also have a CX. So all three will have three force components at C, the thrust bearing. At the bearing, we'll impart any couples onto the shaft. Right? And why are no couples going to be imparted on the shaft? They're perfectly or they're properly aligned. When that's the case, we ignore the fact that at a bearing we could not rotate around Z or around Y. When they're properly aligned, it makes it such that there's no reason it needs to rotate around those axes. So the proper alignment says no couples are going to be imparted at C, and it would also say no couples will be imparted at D, which we'll get to in a second. So at point C, those are the proper forces, Cx, Cy, and Cz, and then no couples. Now we go to the bearing at D. This is a journal bearing, so what forces, what translations are prevented due to the journal bearing? Right, the Y and the Z direction, the same as no matter what type of bearing, it would not be able to go normal to the longitude of the shaft. So we'll have a DZ and a DY. This is a journal bearing. The journal bearing allows the shaft to move along its longitude, or the shaft to move through the bearing. So because it does allow that motion at D, there will not be a force at D in the X direction. And we just discussed, because there's properly aligned, there'll be no couples at D either. So D will have those two forces in the Z and one in the Y. Right, so our supports are all there. Because we're in 3D, I want to now include the coordinates of these points to make the next step easier. So from my coordinate system with the origin at B, C is at 50, 0, 0. D is at 350, 0, 0. F is at 400, 0, 250. These are all in millimeters. B is at the origin, so I won't mark it. H is located on the y-axis, so at 0, 250, 0. And the point A, I would just have to do a little bit of work. I know it's 30 degrees from the z-axis, and I know that the length of AB is 250 millimeters. So along the z-axis, it will be 250 cosine 30 degrees. And along the y-axis, what's that? Sorry. So 250 cosine 30, and along the z, 250 sine 30. So in this case, it goes along 0 in the x direction. It's 250 sine 30, which is approximately 125 in the y direction. And in the z direction, 217. And yeah, B is at the origin, so all of my points are marked, which will make the equation step easier to go through. Yeah. I didn't. It doesn't actually do anything for us, so it's there, but we actually don't have to deal with it. It's just the elbow. Questions on the complete now free body diagram. I have my dimensions in the form of coordinates. I have my support forces marked. I have that rope marked, and I have my coordinate system also included. Again, notice anywhere there was a support, there's some type of reaction that has to be included in my free body diagram. Right, first thing, we do want to find the unit vector from A to H, because that tension is not only in X, Y, or Z. All of our other forces are only along X, Y, or Z. I broke my own rule a little bit here. I rounded probably too much, but you should get about 0.5 J minus 0.87 K for the unit vector from A to H. This allows us to easily do our force equations from our free body diagrams. In the X direction, Cx, our AH has no I component. So this is the only force in the X direction, so it turns out to be 0. In the Y direction, we have a CY. We have DY. We have negative 400. And we do have a piece of the tension. We'll have 0.5 times its magnitude. Three unknowns in my second equation. And when I sum forces in the Z, I have a CZ and a DZ. And I have another the other piece of my tension, 0.87 times that unknown tension AH. Between equations 2 and 3, I now have 5 unknowns, but only 2 equations. I've used equation 1 to find the value of Cx. So 4 through 6, I don't think we'll have time to do all of this. So I'll give you the answer. You can work through the rest of it. We want to take the moment around a point, and we know it's going to be equal to the 0 vector. So which points, if we only look at the free body diagram for now, which point looks like the best one to take it about? Right, C, because it does have 3 unknowns there. It does turn out Cx is 0, so really there's only 2 things left we don't know. If, with that in mind, C or D would be a good choice. I think C, just based on the picture, is a better choice here. If we take the moment around C, that means that we need to first account for any couples that are acting on this. There are no external couples here, so we don't have to worry about that. But we will have a moment caused by every force that's not acting through C. So we'll have RCD crossed with dy and dz here. I'll just call it d hat for now. RCF crossed with the negative 400J from that applied load. And there'll be a moment from the tension, which will be RCA crossed with TAH. Unfortunately, this is 3 cross products that we have to go through here. Some of them are easier than others since this only has a J component. These position vectors, some of them only have zeros for some of the components, so it's not too bad. So quickly, I'll just write out these 3 cross products. From C to D, we have to go 300 in the I. And then this D, when I write it in its component form, this is where I can write it as dy and dz. Here, I'll have a negative 400J. And to go from C to F, I need to go 350, 0, 250. Now here, at this point, I don't know the magnitude of TAH, so I can put it into my cross product with that unknown value. So I'll first have RCA, which will be negative 50, 125, 217. And now for my force row, I have to keep my unknown magnitude. So the J component of TAH is 0.5 times its magnitude. So 0.5 TAH is the J component for that force. And then negative 0.87 TAH will be the K component for my tension. So there will be that unknown that comes out when I go through my cross products. Just so you have an answer to compare to, if we go through the solution step, you should get, well, Cx is 0. From the moment equation, the tension is 462 newtons. Cy, you get a negative 335 newtons. dz, you'll get a negative 66.7. dy, you get 505 newtons. And cz, 467.